Hello students, welcome back. Let's go to section 4, variation of parameter. Before starting, let me give you a brief overview what this is all about in a little bit more general environment. Here we go. Let's consider the situation. y1, y2, y3, and y4 are linearly independent solutions of a homogeneous linear ODE, L of y equals 0. Now, if this ODE has order 4, then this is a general solution. However, what if this has order 5 or higher? In that case, this is not going to be a general solution. It's a solution, yes, because it's a linear combination of the solutions of a homogeneous linear ODE, but it's not a general solution. There are more linearly independent solutions, like y5 and y6, things like those. Now, how do you find those? One way to do that is to consider this linear combination. Start from there, and then change these coefficients around. But C1, C2, C3, and C4, they look like constant. Indeed, if I use linear combination, then they are constant. So let's change the characters a little bit. Instead of C1, let's use U1. So instead of C1, C2, C3, and C4, let me change those into U1, U2, U3, and U4, which are now changing around. And then take the derivatives using the product rule and so on, and put it back into the original equation here. Maybe there are some additional condition. You can impose those as well. And then eventually you're looking for U1, U2, U3, and U4. Once you do it, then you have a new solution, y5. Maybe you can get 2 of them depending upon what other solutions or what other conditions are there, and maybe y5 and y6. This kind of method is called variation of parameter. Let's go back to this original linear combination expression. These are constant coefficients, C1, C2, C3, and C4, so I cannot change them around. You see, variation of constants, that's an oxymoron, isn't it? Constants stay the same, they stay constant, so you cannot vary. So variation of constant does not make any sense. Variation of parameter, now U1, U2, U3, and U4, they are moving around, they change their parameters. So that's what this variation of parameters is all about. Another application is to find a particular solution of a non-homogeneous equation. In this kind of environment, we are looking for yp. But then again, how do you find yp? C1, C2, C3, C4 are all constant, then you cannot really get anything there because that's going to give you another solution of this original L of y equal to 0. But if you have y1, y2, y3, and y4, which are expressions of t, which are moving around, then maybe you can get yp. And that's another application of variation of parameter. In any case, the key is to change these coefficients of all this linear combination into parameters. So let's see. Let me take this kind of expression here and then change this into okay, like this. Okay, like this. Change those constants into parameters, then move those around, and then find out U1, U2, U3, and U4, depending upon additional circumstance. This is the essence of the variation of parameter. Okay, I guess I spent a bit too much time talking about the environment. Let's go directly to actual problems now. Let's begin with the simplest possible case. Just one function, so instead of some big linear combination here, we just have u times y1. That is the simplest case. In that case, we can take derivatives and then plug back into original equation, and you can find out u. Here's an example. y2 is u times y1, which is u times, let's see, in this case, y1 is given as e to the t power. Alright, so y2 prime, how about that? What's the derivative? You can use the product rule, right? So you get u prime e to the t power plus u, and the derivative of the second function stay the same because exponential always stays the same. How about the second derivative? Product rule here and product rule there. So y double prime e to the t power plus u prime and another e to the t power because derivatives stay the same. And another product rule here, u prime e to the t power plus u times e to the t power. That's the second derivative. And let's see, these two are the same. So I can put those two together like this. And that's the second derivative. And that's the first derivative. And this is the original. Okay, put everything back into the original equation here. That's the original ODE. Okay, and then this is a second derivative, and this is a first derivative, and that's the original. Okay, here I'm gonna put in this. And then here I'm gonna put this blue. And then in place of y here, I'll put this in. So red get to red, blue got to blue, green got to green. And then break over all the parentheses, simplify, take those like terms together. You're gonna get a simpler differential equation. You have u prime, and u double prime. Here you have y prime, y double prime. Looks like this is not going to be any simpler than the previous, but it turns out okay in the end. It'll turn out the u part will always disappear, and that's going to be left as a homework. Okay, these are the derivatives. And then if you plug all those into the original equation, we get this. And then exponential is common everywhere. So divide everything by exponential, and yes, I can do that because exponential is never zero. That results in the second line. And then take the like terms together and so on. We have this kind of simplification. And in the end, we have this kind of simplification. So what did you get? A second order linear ODE became a first order linear ODE. Do you see it? Second derivative, first derivative, but no original, so this is actually first order. So this is a reduction of order in action. So many people call this method a reduction of order method. Me, I prefer to call it as a variation of parameter. Deep down, variation of parameter is actually hidden, especially if you have more than one functions here. If you have some linear combination there, then that's really variation of parameter. Anyway, okay, this is linear equation. Excuse me, it's not linear. First order differential equation. It's linear, yeah, but the key is first order. So you can use the method of integrating factor, divide by the leading coefficient, and then get the standard form. And then this is p, right? This is p of t. So you can take the antiderivative, get capital Q, and e to the q power is the integrating factor. Here's the computation. Take the decomposition by partial fraction, not too bad. And then take the antiderivative, t log of t minus 1, and then e to the q power e to the t power minus logarithm. So it's exponential over e to the log. Exponential and log cancel each other out. We end up with this fraction here. Let me expand the font a little bit. There are too many fractions and exponentials here. So, does everybody feel okay about this computation? Oh, one more thing. When you take the antiderivative, you're not looking for arbitrary constant here. Arbitrary constant comes only at the very end. You see, whenever you do c1y1 plus c2y2, where c1 and c2 are arbitrary constant, that's when we have arbitrary integral constant. Anything before that, we don't need anything because basically you're looking for y2, which is a specific function. So we don't need to consider integral constant. So the simplest possible is of course 0. So I just disregard the integral constant here and then get this kind of computation. So okay, that's the integrating factor. Multiply that to both left-hand side and right-hand side. Multiply that to the right-hand side. I don't have anything because 0 times something is always 0. That's nice. How about the left-hand side? It turns out we have the derivative of the integrating factor times u prime, this term here. So we can take the antiderivative, and that's going to be my u prime. By the way, when you take the antiderivative here, we began from 0, so if you take the antiderivative, you get c. And here, instead of taking c equal to 0, I took c equal to 1. Why did I do that? Most of the time, if you take the antiderivative, you want to keep simple. So plus c becomes just 0 is usually the best, but this is one of those exceptions. If you take c equal to 0, then when I divide this one away and multiply the reciprocal, you have that multiplied by 0 and it disappears. So we lose information. So this is one of those exceptions. If you keep it at 0, then I'm going to lose information. So let's go to the next simplest number, and that's 1. So 1 times that, so we get this. I could have selected, say, 3/5 here, 3/5 times this. That's fine, but then again, why would I make it overly complicated? 1 times that is just fine. No 0, because we have to multiply. It should not be 0, otherwise all okay. Alright, u prime is this, so take another antiderivative, and that's going to be my u, and here plus c is going to be just 0. It's okay because I'm not multiplying anything. So we found out u. We wanted to find u so that y2 is u times y1. So we found out u, negative t times e to the negative t. So let's find y2, which is u times y1. And look at this computation, you get negative t. So that's the second solution. If we take a linear combination of the two, then as a matter of fact, maybe you should have this. But it's okay because c2 is an arbitrary constant, so this negative, that'll be eaten up by the c2. So I can just remove this. But if you're really a purist, then you can write negative here. No, I'm not a purist. So there goes the arbitrary solution, or there goes the general solution, excuse me. C1 and C2 are arbitrary. Okay, that's an example of the first example of variation of parameter or reduction of order method. And I guess we have just enough time for a part of the second problem here. Let's try that. Now, have you seen this equation before? I hope everybody remembers. It's this one. This one down here, part C. And what did you get if you use the Laplace transform method? This is what we end up with. Oh, actually no, sorry. I showed you too much. I gave away the answer. Okay, that's what you get. Sine of t over t. You get that answer if you use the Laplace transform method. Now, the other solution, you probably saw that, cosine of t over t, and that's going to be the answer here, but pretend you didn't see it, and let's find out. Okay, let's set up the variation of the parameter, and u times y1. I don't have anything here, so the linear combination is just c times my function. So change that constant c into parameter u. Okay, there you go. And then we take the derivative. Using the product rule and quotient rule, we get this. Oh my goodness, quotient rule. It's a tedious computation, but here we go. Now the second derivative. Hey, what can I say? There you go. Good luck. By the way, all these computations are elementary. Just tedious. So I'll just trust you could follow. Okay, alright, and then plug everything back into the original equation there. So this whole expression goes here, and then this expression goes over there, and this one goes here, and then try to simplify all that. And this is what you get. And if you simplify, you're going to get this, and eventually this entire part will drop out. Why does u always disappear? That's something I'm going to leave as a homework problem. Turns out it always disappears. So what do you have? Again, we have a reduction of order. We began from the second order linear ODE, but we ended up with a first order linear ODE. Yes, we have u double prime, but I don't have u, I just have u prime, so this is first order. And this time I decided to use the separation of variable. Yes, I could have used the integrating factor, but the right hand side is 0. In that case, I can use the separation of variable. Besides, I used the integrating factor in the previous problem, so this time let me change around. Let's use the separation of variable, and this is what you get. And taking the antiderivative of both sides, you're going to get log of u prime equals to log of cosecant squared. So you get u prime is cosecant squared. I'm going to leave the integration, the detail of the integration to students. Eventually, what you get, taking another antiderivative, you get negative cosine of t. We have plus 0 here. As a matter of fact, we have plus c, but we're looking for any specific solutions, so I don't need to worry about any kind of constant here, so let's keep it as plus 0. Alright, that's my u. So u times y1 is what we want. And y1 is sine of t over t. So let's go ahead and calculate that. Cotangent of t times sine of t over t. So we have cosine of t over t. We have this negative sign here, but that's okay because, if this had been negative here, no problem there because this c2 will be, this c2 is arbitrary, so it'll eat up any negative sign there or any other coefficient. So it's okay to disregard the sign, and then we have this general solution there. By the way, sine of t over t is okay because if you take the limit, t is going to 0, then this whole thing is going to 1. But this one is undefined when t goes to 0. So y0 is undefined here. So this part does not have valid Laplace transform. So the Laplace transform method didn't find this part. It found this one, yeah, but not that one.